Hi everyone. In this video, we are going to discuss about Wein bridge oscillator. Wein bridge oscillator is one of the RC type of oscillator, and it is also called as audio frequency oscillator. Generally, the Wein bridge oscillators, it will be used in the frequency range of 20 to 20 kilohertz. That means Wein bridge oscillator works in the frequency range of low frequencies. And as you can see, has two transistors. Each transistor will producing 180-degree phase shift, and totally we people are getting 360-degree phase shift or 0-degree phase shift for the oscillation from your transistor part alone. The name of the oscillator, it came from the Weinstein bridge connection, which we are using as a feedback network in this circuit. As I already said, uh, it has a RC circuit as a feedback network. So the RC bridge circuit, it is also called as lead lag network. As you can see, in the bridge circuit, the resistance and capacitance are connected in terms of R1 in series with C1, R2, R4, R3, everything is parallel with C2. So this setup is used as a feedback network with 0-degree phase shift. That means in your Wein bridge oscillator, the feedback network will not provide any phase shift. The total phase shift of 360-degree, it will be taken care by the transistor part alone. So amplifier setup will provide the 360-degree phase shift. Feedback network, it will provide only 0-degree phase shift. And you can see in the diagram, the output of the second stage supplied back to the feedback network, and the voltage across the R2 and C2, it will be fed as an input towards the transistor Q1 first stage. And the transistor Q1 act as an oscillator as well as an amplifier, and the transistor Q2 here, it is act as an inverter to produce the 180-degree phase shift in a proper way. And the Wein bridge oscillator, it is different from other oscillator with the application of feedback. It's nothing but other oscillators only supports for the positive feedback, but the Wein bridge oscillator, it has some special function. It supports for both positive and negative feedback. The positive feedback is applied through R1, C1, R2, C2 to the transistor of Q1. And the negative feedback is applied through the voltage divider to the input of the transistor Q1. And this R3 and R4 are used to stabilize the amplitude of the output. Now, let's discuss about the working principle of Wein bridge oscillator. As you can see in the diagram, by applying DC supply, the circuit set an oscillation by any random change with respect to IB current. The variation of IB is amplified in the collector circuit with a phase shift of 180-degree. So the output of the transistor Q1 is fed back to the or fed back as an input to the base of the transistor Q2 through C4 capacitance. At this point, another 180-degree will be phase shift will be produced by the second stage of the transistor. So at the output and the collector of the second stage amplifier, we can able to get 360-degree phase shifted output. Having been inverted twice, the output will be in phase with the signal input to the base of the transistor Q1. So a part of the output signal, a transistor Q2 is fed back to the input points of the bridge circuit, and a part of the feedback signal is applied to the emitter resistance R4 where it produces negative feedback. Similarly, a part of the signal is applied across base resistor R2, which can able to provide positive feedback. So at the desired frequency, the regeneration is mainly, that means the positive feedback, it will be slightly more than the negative feedback application. So at the end of the output terminal, you can able to get the sustained oscillation and a particular desired frequency. So this is how the Wein bridge oscillator is working to produce the desired frequency. And now let's see the mathematical analysis of Wein bridge oscillator. So this is a simplified version of your feedback network. R1 and C1 is connected in a series way, and R2 and C2 is connected in the parallel way in your feedback network. So now we are going to simplify this R1 and C1 in terms of Z1 and R2 and C2 in terms of Z2. So according to the connection, the Z1 value will be described in terms of R1 plus 1 divided by j omega C1, and by simplifying that you can able to get this structure with respect to your Z1. And Z2, it will be connected, R2 and C2 will be connected in a parallel way. So Z2 is equal to R2 parallel with 1 divided by j omega C2. By simplifying that, you can get this kind of values with respect to Z2. And this is furthermore simplified diagram of your feedback network in terms of Z1 and Z2. Now, when you see your simplified diagram, it will look like a potential divider. So, with respect to your Z1 and Z2, we are going to apply potential divider rule for obtaining V0 value. So, V0 is equal to AVI Z2 divided by Z2 plus Z1. And we already predicted the values for Z2 and Z1 by using your simplified diagram. Now, we are going to substitute the values in your V0 equation. After providing your values for your Z1 and Z2, by simplifying your R2 j omega C2 plus 1 term, we are going to get your V0 value like this. Now, furthermore, we are doing the simplification with respect to R1 plus 1 divided by j omega C1. So, when we are doing like that, we can able to get the output voltage V0 in this way. The next step, we are going to interchange the Vi value with respect to V0. So V0 divided by Vi, that is equal to A R2 j omega C1 divided by the denominator term, what we are having here. It will come in the same way. And by multiplying your denominator terms, we can able to get your V0 divided by Vi value in a remodified way like this. And we well known about it, by simplifying your imaginary values, we people can able to get a better frequency calculation. So to do that, that means for reducing the imaginary part, what we are going to do means we are going to multiply your denominator and numerator and denominator with respect to minus j. When we are doing that, in your numerator term, we can eliminate your j value. So A R2 omega C1 divided by j omega square R1 C1 R2 C2 minus j, and this imaginary values is also going to get cancelled. So you can able to get omega in the bracket R1 C1 plus R2 C2 plus R2 C1. So now this is your gain calculation with respect to your Wein bridge oscillator. That means V0 divided by Vi ratio will be like this. And from this, for obtaining a desired frequency, first what we are going to do means to determine the frequency, we are going to equate all imaginary part is equal to 0. So as you can see in the equation, the imaginary part, it will be related to your first and second terms. Now we are going to take it as an input for calculating F value. So omega square R1 C1 R2 C2 minus 1 is equal to 0. When you are interchanging and simplifying that, you can able to get the values of frequency F is equal to 1 divided by 2 pi root of R1 C1 R2 C2. In most of the cases in your feedback network, the resistance which we are going to use, it will be in a same equal values. So if R1, R2 is equal to, then the same value means we can take it in terms of R resistance. If your C1 and C2, it will be in the same value, means you can take it as a C value. Then, so R1 and C1, R2, C2, everything is the same value, means you can simplify the frequency equation like this. F is equal to 1 divided by 2 pi RC. Now, this is the frequency formula for your Wein bridge oscillator. And to determine the conditions of oscillation, what is conditions of oscillation? It is nothing but based on what category we people are obtaining this desired frequency, that we have to find it out. So that is called as a conditions of oscillation. So for finding out the conditions of oscillation, we are going to equate all real part is equal to 0. That means we are going to equate all the real parts in this equation with respect to 0. So V naught divided by Vi, that is equal to 1, that is equal to the remaining values of AR2 omega C1 divided by omega R1 C1 plus R2 C2 plus R2 C1. Now, by multiplying and interchanging the terms with respect to 1, you can able to get the simplified values like this: R2, R1C1 plus R2C2 plus R2C1 is equal to AR2 divided by 1. And finally, you are going to divide all the RC combination with respect to R2C1. You can able to get the gain value in terms of 3. Now, we will know about it to get a sustained oscillation, we should satisfy any one of the Barghosen criterion. So, based on that, by taking A beta is equal to 1 and applying the values of A is equal to 3 in this equation, we can able to get beta is equal to 1 divided by 3. So, if beta is equal to 1 divided by 3 and gain is equal to 3 means, then you can able to provide the product of A and beta is equal to 1. Now the conditions of oscillation, it will be satisfied with respect to the calculations. In this way only we people are obtaining the frequency and conditions of oscillation in your Wein bridge oscillator. Now let's see the advantages and disadvantages of your Wein bridge oscillator. So your Wein bridge oscillator, it will works under the frequency range of low frequency. So it will able to provide low distortion across your sinusoidal output. And the frequency range can be selected simply by using decayed resistance boxes. That means it is able to it can able to provide only low frequency, means we can use some small level values. And by varying the capacitance C1 and C2, you can vary your frequencies of oscillation. And by varying the frequency, you can get overall gain in a high value. And the next thing, the disadvantages is the circuit needs 2 transistors. So the circuit structure, it will be a little bit bulgy, and the maximum frequency output is limited because of the amplitude and phase shift characteristics of the amplifiers. We cannot able to get high frequency values in this Wein bridge oscillator. Thank you.